Today we are going to continue with the local analysis that we started dealing with in the last two lectures. And let's start by taking one step backward and trying to remind ourselves what we actually did and what kind of propositions we have made. So our canonical example is the area equation, and we have tried to analyze it to write the solution as a power series, like y equals to sum from n equals 0 to infinity of a n x to the n, where x was actually okay. Oh, so no, I would like to say something else. We did two things. One of them was a standard, like what we did, what you did in I guess second year of the undergraduate studies, right? We started looking at the behavior of this at the vicinity around x equals 0. So this was around x equals 0. We wrote that, and we calculated an. We found an explicit formula for n. This is, and we conclude that this series converge for any finite x. So it's for every x smaller than infinity, this series converge. Because the first of all, 0 is an ordinary point. 0 is an ordinary point of the area equation. A. B. 0 is B, and it does happen that the solution is analytic everywhere in the complex plane, except when x goes to infinity. Then we did something else. We looked at the same equation, but now we want to expand it as x goes to infinity. And we were able to write now that y is asymptotic to something like x to the minus 1/4, e to the plus minus 2/3, x to the 3/2 times w shall x, and we were able to calculate w shall x of x. So w of x is again sum of n. Now it's a n x to the minus 3/2 n or something like that, and we know how to calculate what the a n's are. Right? The same way we have calculated here the an by a recursion formula, we were able to calculate here the an. What's the problem? The problem is that while this series is a converging series, it's a Taylor series, this series does not converge because the an here, an goes like something like x to the power of n divided by n factorial squared, if I remember it correctly. We analyzed that. And here it turns out that an is going like something like some power of x, right? X to the minus n, again, up to factors and so on, times n factorial. And the n factorial wins against x to the minus n. Right? And therefore, this is an asymptotic series, and we define we try to make clear the difference between an asymptotic series and a Taylor series, right? So the idea is that in Taylor series, we are saying that if the series is a Taylor series, right, and the series is y is equal to sum from n equals 0 to infinity of a n x to the n, then we can define Sn, which is a sum from n equals 0 to infinity of to capital N of an x to the n, right? The partial sum, and the Taylor series satisfies a very simple relationship that the limit as capital N goes to infinity of Sn is 0. Of the actual function y minus Sn is going to 0. Right? So if you take more and more terms, at the end of the day, you converge to the right answer. Right? Maybe it takes many terms, but it works. Right? On the other hand, this is Taylor series. If we have an asymptotic series, in an asymptotic series, all we know is that y minus Sn is y minus Sn is negligible with respect to Sn to the an plus 1 to the next term, whatever is the next term, right? I wrote it like that, but it may be 3/2 of n plus 1 and whatever you like, right? As x goes to x naught, in our case it goes to infinity. So the asymptotic series should not converge by any means. All it can do, but we know that the next term puts a bound on the accuracy of the series as x goes to infinity. Okay, so while the typical behavior of Taylor series, right? Suppose we are thinking about this series. So we have this n factorial down here, n factorial squared. So it goes very fast to 0 when n increases. Now I'm speaking about an x to the n as a function of n. Right? So in such a series, if x is very small, then this is exponentially decreasing, and this is decreasing like, and then we have also the n factorial squared decreasing. So it will be something that goes to 0 very fast. But what's happened if I'm taking x to be, let's say, 3? Yeah, then we have 3 squared, 9, 27. So this is growing, but n factorial is also growing, right? And it's going faster. So it will start growing, but then it will go down and do something. These are the options in Taylor series. In the asymptotic series, again, I'm plotting an x to the n as a function of n, right? And you see that it goes like x to the minus n, right? Now here, when x goes to 0, this was when x goes to 0, and this was when x is much larger than 0. Note that I'm expanding around 0, right? So if I'm very close to 0, I have only a few terms to take, and if I'm farther away, I have more terms to take, but at the end it will converge. Maybe I will have to work out to sum up 100 terms, but it will converge. On the other hand, here, when I have such a series, so what I have, first of all, I am expanding around x goes to infinity. So x naught is infinity essentially. So 10 is closer to infinity than 1, right? So if I'm starting with very big x, then this gives me a very strong decrease, right? I have 1,000, 1 over 1,000, 1 over a million, 1 over a billion, and so on and so forth, until the n factorial will win. So if I'm starting with very big x, close to x naught, then I will get something very big x. Yes. So if I'm starting with very big x, I can take there are many terms, and then it is going to blow up because n factorial will win. Of course, if x equal 1, then I have only the n factorial, right? So it will go directly like this. If x equal 10, maybe it will go like that, or like that, and so on and so forth, right? And the way to extract information from such a series, what can we do with such a series? Okay? There are two ways to deal with that, to extract information. Of course, to sum up all the terms of the series will give us just infinite, will give us nothing, right? So what the way to extract information from such a series, as I say, there are two ways. One of them I didn't show you until now, and I will not show you all. I will show you in a few lectures. What I tried to show you last time was the idea of optimal truncation, which means I'm going to use this behavior, and I know that I can take all the terms until I have the minimal one, so I have to stop one before the minimum. That's the optimal truncation method, and this is what you should do here. But these are the differences between asymptotic series and Taylor series, right? One of them is what we get when we expand around the ordinary point, and this one is what we get when we expand around irregular singular point. Okay? Now, in which case our situation is better? Okay?
It depends.
So formally, if you are a mathematician, then you are saying, of course, here everything is nice, converges, I can calculate in whatever accuracy I want, and I mean, clearly it's better than all this weird procedure, right? However, what's happened when you try, now you're a physicist and you want numbers, okay? So you calculate, okay, you want numbers. So this is y of x divided, say, by the sum from n equals 0 to 10 of a n x to the n. And this is, say, x, but in units of, in logarithmic units. Right? Now, what is that? This is the ratio between the true answer and the first 11 terms in the Taylor series around 0. You see? You calculate the first 11 terms and you divide it. Now, if this is, if life are good, then it will be 1. Right? The closer this is to 1, the better our life. Right? So now I'm going to the Holy Book of Mendel and Rosag, page 92, and they have a diagram showing that. So up to 10, it goes like that. Now this is 100, and slightly before 100, I did it slightly after 100, so slightly before 100 is doing something, get completely off. Okay, these are the first 11 terms of the series. So if you calculate it for 10, it's fine, but for 50, it's problematic, and for 100, better you will take like the first 100 terms, not the first 10 terms, 11 terms. Okay? On the other hand, now let's plot something else. Let's plot y of x divided by x to the minus 1/4 e to the minus 2/3 x to the 3/2. So what is that? This is this expansion when I took w to 1. So I'm taking only the first two terms, the physical optics term, first two terms that were we can calculate very easily in the expansion around infinity, right? So how this looks like? Well, from infinity to 100, I need another color. Right. Okay. So, of course, from infinity to 100, it's okay. Around 100, it goes to something like, I don't know, 0.8. So this is 0.8. Goes like here. Then it goes up and end up at 1.6. Now, this is 10 to the minus 4. Okay? You see? This is 10, this is 1, 10 to the minus 1, and so on. It's doing something like that. So you see that an approximation that is, I mean, expansion around infinity, give me only 20% error until I get to 0.01, and give me 60% error at 10 to the minus 4. That's fantastic, right? So from the point of view of mathematics, definitely this is the right way to live, and this is these are suspicious tricks. But when you think as a physicist and you want, you know, the easy and dirty way to get the answer, the irregular singular points are much better than the ordinary points. Good. Okay. Now, a few formal and quasi-formal statements about asymptotic series. Number one, an asymptotic Taylor series is unique. Let's speak about Taylor series. Taylor series is unique. What does it mean? We have a one-to-one correspondence between function and Taylor series. There are no two functions with the same Taylor series. There is no Taylor series that correspond to two functions. No. There is no one-to-one correspondence. No, we cannot find two functions that have the same Taylor series, and we cannot find two Taylor series that correspond to the same function. Okay? It's a one-to-one correspondence between Taylor series and functions. Okay? Now, what about asymptotic series? If I'm saying that w of x is asymptotic to what I wrote, sum over n from n equals 0 to infinity of an times x to the minus 3/2 of n, yes, this was the Taylor series, the asymptotic series that we expand as x goes to infinity. Or maybe it's better to think about series around 0. Let's assume that we have an asymptotic series of some function y around 0, x to the n. I wrote n or alpha, whatever. Right? Something like that. So, first of all, I can find another function. So this is, let's call it y of x. So let's call the other one z of x. That have, suppose this is asymptotic as x goes to 0, right? That have the same asymptotic behavior as x goes to 0. So the same asymptotic behavior may characterize two different functions. Want a proof? Proof, right? To prove that, let's consider that to be y of x, right? Plus e to the minus 1 over x times a. E to the minus 1 over x do not contribute to the power series, because e to the minus 1 over x, all the derivatives are 0 at 0. So it gives you no contribution to the power series. Such a term is called subdominant term. right? And so we can always add a subdominant term to a function and have the same asymptotic analysis, same asymptotic behavior. Okay? So if I did find that this is asymptotic behavior of my function, maybe I missed such a term. This is a word of caution, right? Well, there is a danger here. We may miss such a term, and by taking, okay, is that term important with respect to that?
It depends on the domain.
If x is actually 0, then of course this term is 0. But if x is 10 to the minus 3, right, then perhaps it is not important unless a is huge, right? So it may happen that this term will be important closer and closer to the point we are expanding around. Okay, but so as I said, asymptotic series are not unique. You may have the same asymptotic series corresponding to two different functions. On the other hand, asymptotic series are unique in the sense that every function corresponds to only one asymptotic series. So you cannot find a function y of x which is represented both by sum over n of a n x to the n and by sum over n of b n x to the n. Right? There is no such thing. And therefore, this was the reason why we were able to compare, to ask the series to be equal to each other term by term, because there is a uniqueness in that sense. Okay? Okay, so do you understand?
No.
No.
How does it show that?
There are functions and there are series. Right? Okay? In Taylor series, there is a unique no function have two expansion, no expansion have two functions. Right? In asymptotic series, one expansion may have two functions, because if that function differs by a subdominant term, you're not going to see that. But this may happen for asymptotic series, but this cannot happen. One function cannot correspond to two different series. Yes.
So the loss of information is just in one direction. That's what you're saying.
If you want to speak, well, okay, fine. I'm fine with that. Okay, another point has to do with can we say that if we have a asymptotic series between y of x and say f of x, where f of x may be, I don't know, some Taylor series or asymptotic series like that, but whatever, can we say that y prime of x is asymptotic to f prime of x? And can we say that the integral dx y of x is asymptotic to the integral dx f of x? Right? Question mark.
Yes.
Okay.
Well,
so there is a branch of mathematics that deal with such questions. So just to let you know what the names are. So the equivalence between, if we are speaking about this, right, the red arrow conclusion, the theorems that are dealing with that are called abelian theorem. And this is usually fine. in general, this is fine. People are using this many times in when doing Laplace transforms, right? When you do Laplace transform, one may assume that the integral from 0 to infinity of e to the minus st f of t is asymptotic to the integral from 0 to infinity of e to the minus st g of t, right? If f of t is asymptotic to g of t as t goes to 0. You see why t goes to 0? Because we have the s that this is okay. So this is the kind of behavior that people are using. These are abelian theorems. A more problematic story is that. So in order to convince you that this is a problematic story, let me give you an example. Let's speak about the function y, which is equal to x squared plus sine of x to the power of 25. Now, clearly, as x goes to infinity, this function is asymptotic to what? When x goes to infinity, this function is asymptotic to
y equals x squared.
X squared, asymptotic to x squared, right? Because x squared divided by this is going to 1 as x goes to infinity. Perfect? All of you agree with me. What about y prime? Y prime will be 2x plus x to the 24 times sine x to the 25 times something, right? And this is clearly not asymptotic to x, 2x, as x goes to infinity, right? Because of this. You see? So it's much more difficult to give a guarantee for the green relationship. And what the theorems that are dealing with that are called the Tauberian's theorem. If you think that I know how to spell Tauberian, Tauberian. So Tauberian theorems are those who are dealing with the conditions under which one can take the derivative of a asymptotic relationship and it will still be true, right? And it will preserve the asymptotic relationship. Now, although it's problematic, as I try to convince you here, still, when the origin of the whole story is a differential equation, then in most cases, you have no problems in taking the derivative. Why? Because this is a differential equation. The differential equation is telling you that that y double prime is asymptotic to y plus y prime, or I don't know, something like that. And of course, if you have such a thing, right, then you cannot satisfy the differential equation. So in some sense, these are all hand waving, and nothing here is mathematically written in stone, but in general, this is a case. These are, yeah. Okay. Maybe it will be also instructive to give perhaps the simplest example of an asymptotic series. Because we derive this W from, who knows, Bessel, Airy function and it was a very complicated. So let's, in order to maybe I should have pointed this out before, but let's give a very simple example of an asymptotic series. And this maybe canonical example is this is a Stieltjes integral. See? Look at the integral first. Have you ever heard about Stieltjes? Very important mathematician. So Stieltjes was a student in Leiden University, and he wanted to continue to a PhD, but unfortunately he failed in the exams. So they didn't want him to continue his studies in Leiden. But fortunately for him, his father was a very important politician in the Netherlands. And I don't know if they had phones at this time, but he somehow connected, made contact with the university and explained them that it's better for them to continue with Stieltjes. So they gave him a position in the observatory of the university, and he started doing mathematics. And he was this was one of the examples that shows that nepotism is good, because he contributed to many branches of mathematics. And he had a very long and for many years, he was corresponding with Hermite. That was not a polynomial, but a person, before he became polynomial. And Hermite was working, I guess, in Paris, and Stieltjes was had a lot of correspondence with Hermite, and they discussed all kinds of math problems. And then one day, Stieltjes wrote to Hermite and told him that he solved he have a proof for the Riemann hypothesis. Okay? So, of course, although the Riemann hypothesis at the time was not what it is today, it was still, everybody knew that it's a very important problem. And Hermite was extremely excited, and of course wrote to him, please send me the proof, but he didn't. He wrote to him about other things, but he didn't send him the proof. So Hermite wanted to create some incentive, some temptation for Stieltjes to reveal the proof for the Riemann hypothesis. And you know that the Riemann hypothesis is essentially one of its
Millennium math problems?
What?
The Millennium math problem.
Now it's also the one. It's a Hilbert problem. I mean, it has many. At the time, it was what?
I think it's the only unsolved Hilbert problem.
No.
No?
The 16th is also unsolved.
Oh.
Something with general classification of all the limit cycle for some kind of a Lotka-Volterra equation. Actually, I wanted to give it as a project to 2 students at it's Benuti. But anyhow. So I mean, this is a real Z. This is the image of Z, right? And this is the line Z equals 1/2, right? And the idea is that should I call it Z or X? I don't know. Who cares? The idea is that the zeta function have non-trivial zeros only on this line. And if you prove that, this is equivalent of showing, I showed you in the first lecture, I guess, this relationship between the number of prime numbers up to n right? That there is a Gauss estimation for the number of prime numbers up to n, and which is a Lie something, some logarithmic, inverse logarithmic function. And if you prove that, it implies that this minus the estimation of Gauss, something like that, is smaller than some constant times the square root of n, if I remember it correctly. Right? So this, to show that this and to show Riemann, to prove Riemann hypothesis is the same. Okay? So, as I told you, Hermite wanted Stieltjes to have an incentive to reveal the proof for Riemann hypothesis. So he arranged that whoever the France Academy of Science or somebody like that will suggest a prize. Right? Every year they stated a problem and they suggested a prize for the best work on this problem. So he told them, okay, let's suggest the prize of this year for, it was 1891 or something. Let's suggest the prize of this year for the proof for the Riemann hypothesis. Okay? Then Hermite started scratching his head and he thought, well, maybe Stieltjes do not have the actually perfect proof for Riemann hypothesis. Let's try to relax the condition. So he didn't ask for a proof for the Riemann hypothesis. What he asked is a proof that there are no zeros on the line z equals 1. Right? And if you can prove that there are no zeros on the line z equals 1, then you prove that pi of n is asymptotic to the estimation of Gauss as n goes to infinity. Right? So instead of having actual something with finite bound, you want only asymptotic relationship. So, okay, so the France something for something suggested the prize for this proving that, and Hermite, you know, was sitting in his armchair, I guess, and smoking, I don't know, and waiting for Stieltjes to reveal the answer. He never did that. Okay, so Stieltjes didn't send proof. If he had one, then he took this to his grave. Unlike the guy from the first lecture, this is really a big problem. But surprisingly, somebody else sent the proof. And this guy, whose name was Hadamard. Maybe you know the name from gates in quantum computers, right? Hadamard gate. So the same Hadamard. Hadamard was a student of Hermite, and he looked at the idea of, I mean, he was impressed by the prize and worked hard and had a proof. So he didn't, of course, he didn't prove the Riemann conjecture in all its glory, but he proves that there are no zeros here, and therefore the suggestion of Gauss is actually a theorem now, which is a statement about asymptotic relationship of the number of prime numbers up to some very large bound with a function suggested by Gauss. Right, so this was the work of Hadamard. It took him a few years to end up and publish the work because then he became involved in the French politics, and the reason is that his how do you say that, cousin, right, whose name was I guess, Alice? No. Something like, right? Married, not else than. Famous guy that leads to horrible scandal in French politics. Alfred Dreyfus, exactly. So he was a relative of Alfred Dreyfus, and when Dreyfus was convicted, the only guys that really believed that he is not a German spy were his wife and her family. So they tried to help him. I mean, for a few years it was not. I mean, for 2-3 years it gave no result. But then it turns out that I mean, other people came into and showed that he was not the spy. But in any case, that's story of that. And still just didn't do anything. Okay. But anyhow. So this is still this integral. And what you can say about the analytic properties of this integral as a function of x?
Infinity goes to 0.
Okay, if x is 0, this is a perfectly good convergent integral. Integral over e to the minus t. It's 1. Right?
X equals minus 1 over t.
Why minus 1 over t? If x is positive, then it converges even faster. However, once x is becoming negative, no matter how small, right, then we have divergence as at t equals to 1 over x, and the integral diverges. Right? So clearly the radius of convergence of this integral around x equals 0 is what? Is 0. Once you get out of 0, no matter how close you are to 0, bang, the integral do not converge. Right? Now what is the series? So it's very easy. I can write this as the integral for 0 to infinity dt, e to the minus t, times the sum from n equals 0 to infinity. I expand this in a Taylor series. So what I have is x to the n, t to the n, minus 1 to the n. And now I can integrate. Now, what is the integral? Please remind me. What is the integral from 0 to infinity? T to the n, e to the minus t.
Gamma function.
What?
Gamma function.
Gamma function of what?
Of n minus.
n plus 1.
Gamma of n plus 1, which is n factorial. So this is sum from n equals 0 to infinity of minus 1 to the power of n times n factorial times x to the n. Right. And now you see what's happened, right? This sum always diverges because of the n factorial, right? And the reason is because we are trying to expand something around a point where the radius of convergence is 0, right? So 0 is not a point around which we can expand this in a Taylor series. As a result, what we get is an asymptotic series that but however, if x is very small, the x to the n will go exponentially very fast, and I will have to wait for very, very large n for the n factorial to win. So what I'm going to get, by the way, I mean, so now I'm speaking about n factorial x to the n. Of course, there is a plus minus bang bang, but I don't want to plot it. So if x is very small, like x is 0.1, I will have something like that. On the other hand, if x is 1, then it is going just up, right? And if x is a point, if this is like x equals 0.01, so x 0.1 will go like that, That's a typical behavior. And as I said, the best estimate you can get from this series is just to stop at just one before the optimal truncation, so one before the smallest term of the asymptotic series. Okay, so this is a very simple example that allows you to grasp the idea of asymptotic series. Okay, good. Next. Now, we have expanded the A function as a Taylor series around 0, and we did asymptotic when x goes to infinity, which is irregular singular point. Now, how the asymptotics will behave if instead of calculating the behavior at x goes to infinity, I will ask what is the behavior as x goes to minus infinity. Okay, let's try to see what will happen. We are going to start with y double prime is equals xy, and now we write y is e to the s, so s double prime plus s prime squared is asymptotic to x, but we want x to be large and negative. So just to, right, I want to write it like that. I'm not saying what's happened around 0, so it's not that I'm looking just at what x large and negative. Okay? And again, you can check with dominant balance that it's the x prime squared that should be equal, asymptotic to minus absolute value of x. So s prime is going like, no, I don't want this absolute value. Call it x and call it x, and we know that x is large and negative. Okay? So s prime is plus minus square root of x. But now, so what does it mean? This is now
It goes to
plus minus I times the square root of x. You see? Okay? So s is plus minus 2/3 I times wait, what do I want to say is 2/3 x to the 3/2, again exactly as before, but now as I said x is negative, right? So what is that? What is x to the 3/2? Right.
it's I.
Yes, it's I, it's 2/3, okay, so S, so essentially what we have here is y is asymptotic to, and by the way, you can continue it doing the next term, and you find that it will be x to the minus 1/4 times e to the plus minus I times 2/3 x to the 3/2. This is the optical physics expression for the behavior of the area function at the large and negative x, not large and positive, large and negative. Okay? Now, since we want the answer to be real, what we should do?
Take the real part and then
No. If I have e to the ix and e to the minus ix and I want real functions, what I'm doing?
adding.
I'm adding them, I have a cosine and sine. So we expect the y to be x to the minus 1/4 times cosine 2/3 x to the 3/2 or sine 2/3 x to the 3/2. to be more, to give you the exact,
But similar to the Bessel function.
what?
Similar to the Bessel functions.
Yeah, okay. And just to be compared with the asymptotic behavior of the Airy and the Bairy, you remember the Airy, when x goes to infinity, it is going like x to the minus 1/4, e to the minus 2/3 x to the 3/2, right? This is when x goes to infinity. When x goes to minus infinity, it is going like actually, okay, there is an exact asymptotic, so 1 over square root of pi that we cannot get from this expansion because it's I mean, we can always add whatever constant we like, minus x to the minus 1/4 times sine. We are going to use this formula next, so that's the reason why it's important to me to write them. 2/3 minus x to the 3/2 plus pi over 4. And the Bailey, that when x goes to infinity goes like x to the minus 1/4 times e to the 2/3 x to the 3/2 is going at right, like 1 over square root of 2 pi, again this is just convention, minus x to the minus 1/4 times the sine, no, this should be the cosine of course, times the cosine of 2/3 minus x to the 3/2 plus pi over 4. Okay, now so this is the behavior of the Airy and the Bailey. I mean, we are going to specifically need these functions later on, but all I want to show you is that it goes exactly like this. Note that the minus here that I introduced, here you have no minus, but again it's a constant because it's like minus 1 to the minus 1/4. So it's like the 1 over square root of pi, it's a constant. And this and that have the same behavior. Okay. Here there is an idiotic formal problem. Okay? What is the idiotic formal problem? I am telling you that the Airy function is asymptotic to z at large negative x, or that the Bailey function is asymptotic to z at large negative x. This cannot be actually true. Why? Because what I am saying to you now is that the Airy, what does it mean asymptotic? The limit of x goes to minus infinity, large negative x, of Airy divided by this garbage, right? Minus x to the 1/4 sine blah blah blah, is going to 1. Okay? However, this function have zeros. And they are not exactly at the point where the area have zeros. Right? So this cannot be true. I mean, when I divide by 0, it will be infinite. Right? It is not going to 1 because you have zeros. Now the zeros are becoming closer and closer because this is an estimation, right? So this is a negative x, right? This is x, and this is y of x. So y of x is doing, who knows, right? The Airy is doing something like that, and the asymptotic approximation is doing something like, you know, that. But still the zeros are a little bit in a different point. So, I mean, formally speaking, this is wrong, right? But this is problem for the mathematicians to deal with, right? We are happy with that. That's good enough for our work. And if you want to, there are ways to overcome this difficulty. Like saying, not saying that the A is asymptotic to that, but saying that the argument is asymptotic to the argument or something like that. The argument of this sign or that sign, blah, blah, blah. But, I mean, it's not something that healthy persons should spend time on. Okay. So, now, I want to call your attention, however, to a very important thing, a very important observation, which is that when we expand around zero in a Taylor series, if I want now to have it for negative x, what should I do? Just plug x equals -1 instead of x equals 1 and you get the answer, right?
Right.
So Taylor series is converging at a region, at a disk around the, here it's infinite disk, whatever, around the ordinary point, and it's no matter positive, negative, whatever, put whatever number you want for x, I over 2, -1, -5, +7, and just sum up the series. Okay, this is Taylor series. Here we obtain completely different behavior when we take x to infinity and when we take x to -infinity. You see? That's important, a very important observation, which has name. It's called Stokes phenomenon. So, right? So just to repeat what the Stokes phenomenon is. In a more simple manner, suppose we are looking at the glorious function y is sinh of x. Can you remind me how to define this in a more elementary manner?
Exponential.
What is sinh?
Exponential.
Sinh of x is e to the x minus e to the minus x divided by 2. Now I'm asking you, what is the asymptotic behavior of y as x goes to infinity? So clearly, when x goes to infinity, e to the minus x is subdominant, e to the x is dominant, and therefore the asymptotic of y as x goes to infinity is e to the x over 2. However, what's happened when x goes to minus infinity?
The other way around.
It's the other way around, right? E to the x is subdominant, e to the minus x is the important thing, and y will be asymptotic to e to the minus x over 2.
Shouldn't it be minus e to the minus x?
Minus. Okay? Now, so when x goes to infinity, I took this term. When x goes to minus infinity, the important term is that term. Now, here comes the question for you. Now I have, this is the real part of x, and this is the imaginary part of x. So you know that if I am here, then it is this, right? Let's call it A, and this is B. So here it's A, I'm taking x to infinity, but this way.
You can divide it into real part and imaginary.
Very good. I can divide it to real part and imaginary part. Okay? And I have to compare e to the real x plus I imaginary x with e to the minus real x minus I imaginary x. Okay? What is important, the imaginary or the real?
The real.
The real. Right? The imaginary part only gave us oscillations. Right? What's important is the real. So what you say is, as long as real x is positive, right, then I should take the A. If real x is negative, I should take B. What's happened if real x, what's the other option?
0.
Real x is 0. What's happened when real x is 0?
You're in this line.
Think about this function. What's happened to this function when x is purely imaginary?
It becomes the sign.
It's a sine function. And it oscillates and there is no asymptotic behavior. Right?
Right.
So the way people are expressing that, they are saying that in all this region, the asymptotic expansion is A. In all that region, the asymptotic expansion is B. And on the line that's separating them, there is no asymptotic expansion. Okay? Good. Now, let's ask the same question for the area.
Okay.
Okay, now we have the area, and you see, there is, let's call this A, the blue, and let's call this B, the violet. Perfect. Okay? So again, I am plotting real x and imaginary x. And we know that as x goes to infinity, I am doing A. As x goes to minus infinity, I am doing B. What's happened here? Or here?
You go to A, right?
Well, it's a bit more complicated since we have
Very
to
good.
expand the x to the 3/2.
Very good. Very good. Thank you very much. So we have here, let's take the A, right? We have x to the 3/2. Right. So now we can write it as, instead of writing it as real plus image, let's write the x to the 3/2 as r to the 3/2 times e to the I theta, sorry, 3/2 theta. You see? Now, the simplest way to find out where we are switching from one type to the other is to find out, okay, we have, so we want, what do we want? We want theta when 3/2 theta will be equal to pi over 2. Right? Because if 3/2 theta is equal to pi over 2, then what?
Real.
Then what I have here, what?
It's a real part.
No, it's imaginary.
Imaginary.
It will be purely imaginary, and then the area and the area will become something like sine and cosine, and we will have no asymptotic behavior. See? So as long as theta, okay, and of course, this very complicated calculation tells you that theta, actually it's plus minus, of course. So theta is plus minus pi over 3, which is plus minus 60 degrees. Okay? So this gives me, so I'm taking 60 degrees from here. This is 60. This is 60. Right? In all this region, I should use A. And in that region, I I should use B. Okay?
What about the other? Shouldn't you extend the line all the way?
Where?
Well, you're making the. Shouldn't it also be a pi third?
Oh, let's check. This is okay, and for that region, people are usually speaking about Stokes' wedge. This is a wedge. So the asymptotic behavior here is, again, all this is when I'm taking x to infinity, right? So if I'm taking x to infinity through this region of the wedge, I should use the large positive x behavior, and all here, including here, right? And when taking x to infinity, I should use the negative large x behavior. Okay? Yes.
What about the imaginary line? אמרנו
It's
קודם
nothing.
כאילו שעל הציר הזה...
נכון, כי קודם על ה-imaginary line היה התנהגות אחרת. פה, אם תיקח כן, על הדבר הזה, תראה את אותה התנהגות שיש באזור הזה. Okay? So this is Stokes' phenomenon. And because of that, people even in that case are speaking about wedge, and they are showing something like that. But the meaning is everything except the imaginary line, right? Okay, this is, as I said, Stokes' phenomenon. Which, by the way, for example, what will happen if we have something that goes like e to the minus 1 over square root of x, by the way? Okay, please convince yourself that this, here the wedge will be everything except the negative part of so the wedge will be something like that. Everything except the negative part of the x-axis. This is called the cut plane. The plane except the negative x. Okay, so I showed you at the beginning of this lecture, I just quoted a figure from Mr. Bender and Orzag holy book, that show how much the asymptotic analysis is better than Taylor series. Right? The Taylor series, we have first 11 terms. It allows us to go from 0 to 100 to, let's say, 50, and by the way, also to minus 50, because it converges on a disk, right? On the other hand, the asymptotic behavior gave us 60% error even at 10 to the minus 4, although it's an asymptotic around infinity. Right? Much better approximation. Now you can understand the reason. The reason is exactly that the poor Taylor series is forced. I mean, because the mathematicians told him, right, you must imitate the function on a disk around the ordinary point. This may be a very difficult task. Because, for example, you remember that the actual behavior of the area function, it blows up here, and then it goes like here, and it starts doing like something like that. So it's very difficult for the poor Taylor series to account for both behaviors. It must, work hard. And for that reason, it cannot imitate the function in a good manner, right? in an accurate manner. So, for example, if you really want to have a lot of fun, look at what you are using to do analytic work. Mathematica, Maple. You're not doing analytic work. Okay, fine. So, whatever takes whatever you like, and try to expand 1 over gamma of x, right, in a way that it will be accurate up to x equal 5. Now, why? Because you remember what gamma of x is doing, right? Gamma of x is for positive x, it diverges like x factorial, but now it diverges also at 0, and now it jumps to minus infinity, it goes like that, and goes like that, and so on. So so the gamma is not an analytic function at 0, right? But 1 over gamma is an entire function. It's a absolutely and completely and perfectly kosher function for any x, because, you know, these are just zeros of 1 over gamma. So this is a fantastically entire function. However, if you want to write it as sum of a n x to the n around 0, then it has to account for all these crazy behaviors, and it's so you should, if I remember it correctly, you should use hundreds of terms in order to expand to get a reliable estimation for 1 over gamma of 5 using Taylor series. And you know, horrible numbers and all kind of disgusting things. Okay? So this is a Stokes phenomenon, and that's why, and of course, as I said, the poor Taylor series must work on both sides, on a disk. On the other hand, the asymptotic expansion has no problem, because what we are doing here should not be correct here. Right? We are going to infinity on different routes, and it captures the behavior on each route separately. Which is what allows us all this flexibility. Finally, let's speak about inhomogeneous equations. Right? So let's speak about the y double prime is xy plus 1. Okay. This is an inhomogeneous linear equation. Right? What can you tell me about the general properties of the solution y of x?
It's a sum of two solutions.
2, 3.
3.
Right? Because it's some constant a times a of x plus some constant b. No, it's not good to call it constant a and b.
C.
So it will be
C1, C2.
d1 times a of x plus d2 times b of x plus the special solution. Right? Because I can always add these solutions that are solutions of the homogeneous equation without affecting the solution of the inhomogeneous. So we know the A, we know the Bailey, and now, or at least the asymptotic behavior now, and now we want the spatial solution. Let's call it, I don't know, y3 of x. Okay? The spatial solution of the inhomogeneous equation. Now, there is in the book you can find ways to find y3 given the A and the B. How to do that?
Just plug it up.
It's called variation of parameters. If I have y1 and y2, and I have f of x, which is an inhomogeneous term. Here I took f of x to be 1, but I can write x squared or whatever garbage as an inhomogeneous term, right? Then you know that y3 is minus, who knows, yes, y1, yes, y1 of x times the integral up to x of y2 of t, f of t divided by w of t, plus y2 of x, the integral up to x of y1 of t, f of t divided by w of t, dt, of course, dt here, right? And what is w?
The Wronskian.
The Wronskian. So w is y1, y2, y1 prime, y2 prime. Okay? Sounds good until you start trying to plug the area and the Bailey as y1 and y2. And this is, of course, the most horrible thing on earth. Right? So you don't want to do it that way. Okay? What you want to do is asymptotic analysis. So now we assume we want y double prime to be asymptotic to xy plus 1 as x goes to infinity. Right? As x goes to infinity. So, what's the next step? Ladies and gentlemen, what should I do now? Dominant balance. Thank you very much. There are three options. This balance that, but we know what we are going to get from this. This is the this is the expansion of the. This is what we did for the homogeneous case, right? So either this balance that or this balance that. Okay. So either y double prime is asymptotic to 1 as x goes to infinity, or xy is asymptotic to 1 as x goes to infinity. Okay. Let's see. If y double prime is asymptotic to 1, then y prime is going like x, then y is going like x squared. Give or take garbage. Which implies that xy is going like x cubed, which is much larger than 1. So this is inconsistent. Right? So we do not accept this. Inconsistent. So the only other choice is that, which implies that y is going like 1 over x, actually, because, right, y is going like minus 1 over x, so y prime is going like 1 over x squared, so y double prime is going like minus 1 over x cubed, 2. And this is of course consistent because 2 over x cubed is much smaller than 1 or than 1. So this is wrong, this is right. So we have a first approximation. What we called before y3, let's call it y, is asymptotic to minus 1 over x as x goes to infinity. Okay? Maybe this is not enough. Maybe we want to calculate another term. What we should do?
e to the power of s.
Why? What should I do? Okay? What should I do? I should write y as minus 1 over x plus c. I would write this plus c prime, and I would write this plus c double prime. And I will plug again in this equation. So what I will get is minus 2 over x cubed plus c double prime, which is that, is asymptotic to xy. So this is minus 1
Plus c.
plus xc, okay, plus 1. Okay, now the 1 and the 1 cancel by construction because this was the last stage, the last, right?
Solution.
So, and of course c double prime is negligible with respect to z, again by construction, because this is how I constructed that, so I can solve this. So what I found out is that xc is, I don't like this sign, whatever. So c is minus, yes, so fine, yes. So c is minus 2 over x to the power 4. Right, so the next term will be minus 2 over x to the power 4. And can you guess the next term? Will be something like 1 over x to the power 7 and so on. Right? Now what is that? I would like to emphasize. This is the spatial solution. We have 3 solutions to this. I mean, we have not 3 solutions. We have the homogeneous, and this is a spatial solution. So I will write it again as y3. So now we know that y is equals to as I say, d1 times 80, or it's asymptotic, whatever you like, plus d2 times Bailey, or maybe I will write it. I will write the asymptotics. So y is asymptotic to d1 x to the minus 1/4 times e to the minus 2/3 x to the 3/2 plus d2 x to the minus 1/4 e to the plus 2/3 x to the 3/2 plus y3, which is, okay, so we can write it minus 1 over x plus 2 over x to the 4, blah, 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 which is y3. This is asymptotics, the asymptotic solution for the inhomogeneous equation, and you have to try to do that once in order to convince yourself that, I mean, it's infinitely easier to derive this than to derive that. Okay. Now, which term will control the behavior of the solution as x goes to infinity? I have coefficients here, d1 and d2.
The e to the positive x 2/3.
This one.
Yeah.
Yes? So clearly, here we have e to the plus 2/3 x to the 3/2. When x goes to plus infinity, this clearly dominates both this and this. So this and this will be subdominant. If I'm really interested in the behavior of y as x goes to infinity, I can forget about this and about that, and I would like to know only what this kind of thing, this thing is doing. Okay? However, we are physicists, and if this is, for example, a solution of Schrödinger equation, and it happens to be, you know, this is a solution of Schrödinger equation with a constant field. With constant field, yes. So constant field is the derivative of the potential, so the potential is x, so we have something like that. So the time-independent Schrödinger equation with constant field of an electron in a constant field is something like that. The solutions are their functions. However, what will be the behavior of the solution as x goes to infinity? You remember that we have a condition. Now, when we are physicists, we are not interested in the solution of such an equation by itself, but we have some constraint, which is in many cases y infinity is 0. Okay? If y infinity is 0, it implies that we must take this d2 to be 0. Otherwise, it blows up horribly. Right? And then, after introducing that, what we find out, what will be the dominant term? This one. Right? So, because this is dominant with respect to that, this is going to 0 in a probably fast pace, and this is going to 0, but only like 1 over x. Right? So this will dominate the behavior of the solution as x goes to infinity if we have some boundary conditions that tells me that the contribution from the Bailey is 0. Okay? Note that, very interesting, we started with a differential equation and we have solutions and we have constants, right? Because it's an homogeneous equation. But because we are looking at what's going on at infinity, we have this answer without any constant, right? There is no arbitrariness anymore, because what governs the behavior as x goes to infinity, if we want y infinity to be 0, is the spatial solution, and the spatial solution has no coefficient in it. It's not like the homogeneous one. The homogeneous solutions you can always multiply by something, but not the... So in such a case, no matter what is the coefficient d1, the dominant behavior at infinity will be independent of this constant. Okay, I guess that this is what I have. Okay, well, 2.5 minutes ahead of time. Very good. So this was what I like to tell you today. I know that I switched gears from the last time, but it's good to have some time to relax. Now, in what I showed you during the last 3 lectures, I did local analysis, i.e., I expand the solution of a certain differential equation around a certain point, like 0 or infinity. I can expand it around 5. It will be horrible, but in principle, it's the same work, same kind of work. Okay? Now, as physicists, this may be interesting in many cases, but the standard problem, like solving the Schrödinger equation with some boundary conditions. So if we have boundary conditions, we cannot use local analysis, because local analysis tells me what is the behavior here and what is the behavior here. But boundary conditions tell me that the behavior here is connected to the behavior here, and I have no way how to connect them. Right? To do that, we should use perturbation theory. The way I showed you, what I showed you in the first lecture, the example was x to the 5th plus, let's say, epsilon x equals 1, right? So the epsilon, it's like having the Schrödinger. Suppose we have something like y double prime of x plus y of x times x squared. This is something like harmonic oscillator, plus epsilon x to the 4 y of x equals e y of x. Right? Something like that. That's like an anharmonic oscillator. So here, to expand this around x equals 0 or x equals 1 or x equals infinity is not good, because we want some global solution on which we can impose the boundary conditions. So what we need is to expand not in x, what I did until now, which is local analysis. I want to do global analysis and to expand in epsilon. And this is what we are going to do from the next lecture on. Thank you very much. And of course, I should say again that maybe I told it only to individuals and not to everybody. This is the holy book that every Jew should have at home, and kiss every time you open it. I think that I never encounter a book that has so much useful information per unit area than this one. That's my impression.
Hello everyone, today we will cover 3 topics. The first one will be local analysis. So we already know how to solve second order differential equation of this kind. So, and we can find the solution in the regular points, in the irregular singular points, and in singular regular points. So the question is how to now solve inhomogeneous differential equation. So in the first part of the tutorial, we will discuss some methods, how you can find the general solution for this equation. Obviously, the first step is to solve the homogeneous differential equation. So we know the methods, and from known methods we can find y1 of x and y2 of x. These are solutions of the homogeneous. And then we need to find the particular solution of inhomogeneous differential equations. And usually, near the singular point, the particular solution often behaves better than these two solutions, general solutions of this equation. So, and therefore, in many cases, we can try to find the particular solution as some smooth function. Okay. So it can be polynomial. Usually it's polynomial because if we assume that a particular solution is a smooth function, we can represent it as a Taylor series. And Taylor series is sum of polynomials, right? So, and the x naught here is singular point. Okay. So let's begin our warm up with something really simple. The first example will look like this: x squared y double prime minus 2x y prime plus 2y equals x cubed. Well, we need to find general solution of this differential equation. So the first step is to find two solutions of homogeneous equation. Right? And you can see that this is actually the earlier Cauchy equation. Right? So we can try to find the solution in this form. So we just plug in this solution to the homogeneous equation, and what we will get, x to the r minus 1 minus 2 r x to the r, right, plus 2 x to the r equals 0, right? So then we have r squared minus 3r plus 2, okay? And the roots of this quadratic equation is 1 and 2. So the two solutions are of the ordinary homogeneous equation is c1x plus c2x squared. Okay. And then we need to find the particular solution of the inhomogeneous equation. Okay. So as I said before, usually we can find the particular solution in the form of polynomial. So what do you think what polynomial would be right guess in this right hand side? X cubed. Okay. So if we plug in these two equations, we can define the find what is A, right? So we will get so after 2 times the 6a x to the 3 minus 6a x to the 3, right, plus 2a x. So this and this away, and a is 1. So in this case, the solution is that's, I mean, that's kind of examples you've seen many times in the course in bachelor degree, right? Just simple methods. Okay. So let's look at another case. We will keep this part the same, but I'll change the power here to the 2. Okay, this solution is the same because we didn't change the left-hand side. But now one of the solutions of homogeneous equations has the same power as right-hand side. So that's why we cannot find the particular solution in this form. Why? Because if we plug in this into the left-hand side, we find that A equals 0. So what can we do? Yeah, like the same thing. What we would do if we have repeated root. If we have repeated root here, the first one would be just, let's say, 1 and 1. The first one would be x. The second one x1 x. So in the same way we can write here. So we will guess a particular solution in this form. And then we plug this solution to the equation. We'll find that A is 1, and in this case, the general solution is this. Okay. Good. Is this equation has singular points?
Yeah. At infinity.
Okay,
At
this
0.
is irregular singular point.
Regular.
But yeah, you're right. So x equals 0 is a regular singular point, right? Okay. Good. Let's look at the next example. This one a bit harder, but we can manage it. Okay, so again we need to find the general solution. So the first step is to find the solution of homogeneous equation. Okay. In this equation, x equals 0 is irregular singular point. Iso. So how we can solve it?
Asymptotic. Substitute y equals e.
Yeah.
E to
We
the power
We
s.
call it WK B-like method. Okay? And we assume that solution has such a form. Okay. And then we plug this to this. We need to calculate the first derivative and the second. When we plug this to this, we will get x cubed s double prime plus s prime squared plus 1, right? Can you solve this?
Well, we
dominant.
Yeah. But what I need to do before that?
Divide by
Make it asymptotic.
Yeah. So I cannot solve it like that. I need to change this equal sign to asymptotic too. Okay. Good. So then let's divide both parts by this. Okay, and then I use dominant balance. Right? So, which term I usually pick?
It's like squared and x and minus.
This and this. So, and s prime square is minus x minus per, right? And then s prime is asymptotic to plus minus I x to the minus 3 halves, right? And then we integrate both sides, and it will be minus plus 2I x to the minus 1 half. Yeah. This is the let's go with zero order approximation, right? We need to calculate. Let's go with s naught.
Okay, well, it's not true.
Hmm?
At 0, we see that it is a s prime prime isn't negligible.
This one?
Yeah. Because it's at 0, so s to the minus 5 halves blows up much faster at 0.
Not a zero, it's to infinity is supposed to be. Nice. No, it's supposed to be the first. When you do x to the power 3, it's supposed to be to infinity, it's give the regular singular
No,
point.
but the irregular single treated is at
No, we're
0.
talking about 0, right?
Yeah,
So,
so,
and,
Zero,
so s prime prime is.
So I picked these two terms, right?
Oh wait, no, you're right. I see what you're saying. I forgot to square it. No, so that's good.
Yeah, so it should be minus 2.5, and here is minus 3.
Good.
So everything is fine.
I have a question just. What do
Yeah.
you say if you take x to the power 3 equal to 0, you get y equal 0. It's not a regular singular point, you have a solution.
Here?
Yeah.
No, I mean, if you divided both sides by x cube, you will have this equation.
Okay.
And because here is not square but cube, it would be irregular single. So this is the S naught, and then we need to find S1, which is the next correction. Right? So we will get S naught double prime plus S1 double prime plus S naught prime square plus 2S1 S naught, and then plus S1 prime square, but it's much lower, we can neglect much smaller. Okay, so on this plus 1, asymptotic. When we plug in what we found for S naught, and as
So
long
it'd be plus 1 over x cubed. Yeah, thanks.
then we plug in, we will have that S1 prime asymptotic to minus 3/4 x minus 1. Okay, then after integration, S1 is minus 3/4 1x. Okay, and then the solution, actually we obtain two solutions. There's for plus and for minus. C1 x to the minus 3/4 e to the minus 2I x to the minus 1 plus C2 x to the minus 3/4 e to the plus 2 e x over in the power minus 1 half. Okay. This is the solution, asymptotic solution for the homogeneous equation. And now we need to find out what is the solution for, what is the particular solution. Okay. And as usual, we can try to find it in a form of polynomial. Okay. We just look at the right hand side and try to find it in this way. Okay. So if we plug this to the original equation, the second derivative is just 0, and then we see that a just 1. So the particular solution is exact, and the general solution of this equation looks like this. So when x approaches 0, here we have sum of two exponents that are actually just sine and cosine, and the closer we to 0, the more oscillations those exponents have. So, but as I said, usually particular solution behaves much smoother than the solutions of homogeneous equations. Okay. The next one, example number 4, looks like this. It's cubed y double prime plus 1 plus x y equals 1. Again, x equals 0 is irregular singular point, and we want to find the solution near this point. Okay, so let's solve the homogeneous problem firstly. For homogeneous problem, we have x cubed y double prime plus y prime plus x y 0. So we can neglect this term compared to this, because x goes to 0, and solve much easier way. the same one. Okay. So we know actually the solutions of this, and I can write it now. Now let's try to find the solution of inhomogeneous equation. Let's rewrite this equation in this way. Just put this to the right hand side with minus and divide it all this by 1 plus x. Okay. And let's try to find the solution in the
Of course, and if x to 0 eliminates the xy, why doesn't it eliminate the x cubed, the second derivative of y?
Yeah, because here we compare y with y, but second derivative may behave differently. So, like we saw here, sometimes s double prime can behave so it even if you multiply by x squared, could be bigger than these terms. But I mean, it's legal to compare those terms. I mean, I couldn't say nothing about this, but when I compare these two, that's okay. So let's try to solve this by iteration method. So on the first step, we will assume that x is small, and if it's small, we can, in the zero order approximation, we can neglect this and this, and in the step number 0, our particular solution is just 1. Okay. On the first step, we will plug this to the equation and calculate y2. So let's call it yp0. So that's 0th step. Here is the first step. If we plug this to the equation, the second derivative of this is just 0. So we will have 1 divided by 1 plus x. We know that this can be represented as a geometric series. So, like 1 minus x plus x squared minus x cubed, and so forth. Then we can use this, right, to calculate the second step, approximation for the second step. For the second step, we need to know the second derivative of this, right? So yp1 prime is minus 1 over 1 plus x squared, and the second derivative prime 1 is 2 1
2x plus 1.
like that. Right. And then we put this into y, and y. The second step will look like 1 minus x cubed, and then this. All of this divided by 1 plus x. Okay. So 1 plus x minus 2x cubed, and this goes to the denominator. 1 plus x to the 4th. Okay. So we see that for the second step we get the value of the particular solution in the first step minus some correction. And we can continue this process. So in this case, for this equation, we cannot actually find the solution in the exact form. So it would be some series, but again, at the singular point x equals 0, the solution, the particular solution is smooth. Okay. And you see that the closer we to 0, the more negligible this additional terms. Okay. So this is the example number 5. So 4. Yeah. Question? No. I guess the last example here. Yeah. Example number 5. X to the 4th, y double prime minus x y prime. 1 over x. Okay, again, x equals 0 is irregular singular point. And firstly, let's solve the homogeneous equation. You see, because we don't have here the function y itself, we can use substitution. So for example, v is y prime. Okay. And then we can rewrite this equation in this form. X to the 4th, v prime minus x v equals 0. If we divide both sides by x, we can get v prime over v equals x to minus 3. And then after integration, here we have e to the no. It's 1 e is minus 2. Yeah, minus 2x. Okay. That is the sign. this is we solved for v, and now for y. So y of x is just integral of this. How we can solve this integral?
Can substitute.
What exactly?
U equals 1 over x.
Yeah.
You get the Gauss.
Then yeah. I mean, we will integrate it by parts eventually. So du is minus dx over x squared. Then dx is just minus e to the minus 2 d. Right? Then integral e to the minus u squared over 2 divided by u squared, here is minus d. Yeah. So then we can integrate both parts. Integrate by parts, right? Let's change this by another letter. So like t. Okay. After
It's 2t dt. You have the derivative.
Yeah, you have to multiply.
2u du. You substitute. You use, yeah, you have another part of.
yeah, sure, yeah. Thanks. Okay, let's skip this. So after one integration by parts, what will I get?
It will be nice to pick
You
the.
get y u to the minus 1 times e to the minus u squared over half plus integral of bell curve.
Yeah. So with a sign, check. There should be e to the so 2. Okay, and then I can integrate again by parts and again and again. But the next term will be will decay much faster than this one, because we say that we're interested in solution near this point. Then near this point, u goes to infinity, right? So here is something small, and the other terms will be smaller because this in the denominator will have a bigger power. Okay. So
But
I didn't
that
get.
That means that it goes faster to 0, like it's getting bigger. Right.
No,
Had-
then x goes to 0, this goes to infinity, right?
How did you get u cubed? Shouldn't it be u to the 1?
No, then you take this to this. It goes like one.
Wait, when you're doing integration, are you integrating u, or are you integrating the 1 over u, or are you integrating the e to the minus u squared half?
No, as usual, when we integrate by parts the exponent, we should use the. This goes to d, right? I mean, you can check math, but the point is that all other terms will decay much faster than the first one. Do you understand why?
They go
All
to
of the-
infinity faster, right?
To 0, not to infinity.
Look about that substituted once 1 over. Okay. When x
Yeah, yeah.
go to
Yeah.
0. Okay.
Yeah.
Sure.
So, and that's why we can say that this is like goes like this. And we just keep this. So y of x goes like e to the minus 0 over 2 u cubed. Or if we go back to the x, it's like x cubed e to the minus 1 over 2 x. Okay. This is the asymptotic solution. And but this is only one solution. Can you guess the second one? All you need to look at the original equation for this.
Constant.
Yeah, just constant. So it's y. So y constant is the second solution. So now we have two solutions of homogeneous differential equation, right? So it's just C1 multiplied by this and C2 just a constant, right? And we want to find the particular solution. Particular solution will have smooth form. Like let's try to this. Okay. When we need to plug this into equation, so y prime of x is like alpha a x alpha is 1. Then x to the 4th multiplied by this. So until x alpha plus 2, right? And the second term x multiplied by y prime just x to the alpha. now we have alpha minus 1, a to the x alpha plus 2 minus a x to the alpha is 1 over x. Okay? This kind of equation. And then x goes to 0, we can compare these two terms and say that this one will go to 0 much faster than this one. Okay, so we can basically neglect them, this term, and we will have this kind of equation. So we neglect the first one and keep only the second one. So the second one is minus xy prime, okay, and 1 over x. Or it's better to say that it's asymptotic to. Okay. Then we say that y prime is asymptotic to minus 1 over x. There's a plus because when we integrate there is another minus. So like this, and we know that now alpha is minus 1, and the particular solution again has the exact form, and it's just 1 over x. And we can check whether it's a good solution or not. So if we plug this solution to the equation, we will get that both sides are equal to each other. So and the general solution is these two and the particular solution. Any questions?
Don't you need to find a specifically?
We wrote here asymptotic too, so in this case we can, because this solution is asymptotic also, so and we can keep this sign everywhere.
Alright.
Yeah. Okay. Now let's talk a bit about WKB approximation, and we'll look at the very useful formula that will help you to solve any kind of let's call it the Schrödinger equation in a minute. Okay. Again, not solve exactly, but asymptotic, of course. So, for example, someone give you this equation. And we want to find the solutions of this equation, then x goes to infinity. So basically near irregular singular point. So, and we assume that this q of x function also goes to infinity, then x goes to infinity. So this is some polynomial, some smooth function. Okay. And you already know the example of this equation. Could be y double prime, I guess minus x y equals, and this is a equation. We know the solution of it, Eigenvalue functions, right? So, and we can, how do we solve it? We use the asymptotic analysis. We again use this formula, right? Plug it in, and then all of these variable things. But now let's do it with some general function q of x. Okay. Again, on the first step, we will assume that solution has this form. Okay. And then we plug this to the equation. We will get s naught double prime plus s naught prime squared plus q equals 0. Okay. On the first step, we neglect this term, and s naught prime is asymptotic to plus minus square root of q of x.
Should it be negative q of x?
So then s naught is plus minus I integral of square root of q of x. Oh, it should be t. Some other variable. Okay, this is the 0th step. Okay. Then we do the same with s1. Okay, with s1, we will have s naught double prime plus 2 s naught s1 prime equals 0. Then s1 prime is asymptotic to minus s naught double prime divided by 2 s naught prime. We know that s naught prime is this. We plug this to this, and so we also need to calculate s naught double prime. S naught double prime. So it's plus minus I over 2. Here is q of x. It's minus 1. So then we have plus minus here, plus here, and plus minus here. So would be with plus sign everywhere, and also I cancels out. So would be 4, and then square root of q of x, and here's q minus then it's just e to the minus.
Shouldn't there be q prime?
No, I don't think so.
When you took the
It's a function
second
of
derivative,
It's a function of t. Not t.
it's a function of x. So when you took a derivative, a second derivative, shouldn't there have been q prime? Because it's square root of q, and q is a function of x.
Yeah, makes sense. And then there is also q prime like this. Yeah. And then we need to integrate this. Right?
It's a natural result.
Yeah. So S1 is minus 1 4 ln q of x. Okay. So then our solution is just e to the so it's 1 over q of x to the 1/4 e to the plus minus I integral square root of q of t dt. This is basically the problem. And if you, for example, solve it for the Euler equation, you can easily find that the solution will look like this. So q just x with a minus sign. Okay, with a minus sign. So then, yeah, here, absolute value. So then solution will look like this. So it's x to the 4 e to the plus minus, and then yeah, because here is minus x, right? So plus minus after integration of square root of x, we have 2 over 3 x to the 3 half. And this is two solutions of the equation. So we can do the same with a different kind of equation, but use the same logic. So again, we need to find the asymptotic solutions of this equation. This is our q of x. Okay, then we need to use this formula. Okay, let's.
This is like your neat polynomials, right?
Yeah, it's a parabolic cylinder equation. Yeah. So let's begin with the calculation of the integral. So in this case, then x goes to infinity. Q of x will be less than 0, right? So let's use another function, v of x, which is minus q of x. So this will be positive. X. Yes. Okay. And then because of q is negative, we will have not oscillating solutions, but decaying and going. So in this case, 1x asymptotic to 1 over v of x 1/4 e to the plus minus integral square root of v of t. Okay, then square root of v. So in this case it's this. And then because we're interested in solution x goes to infinity, we can actually try to approximate this by square root expansion. Actually, we can think maybe it's better to just forget about this 1/4 because x goes to infinity, right? And this is just a number. But we will see, we'll do it properly with this 1/4, and then we compare in the end this solution with this solution, then we just omit this 1/4. Okay. So after expansion, we will have x minus 1/8x plus these terms. Okay. And then we integrate this. Have x squared over 2 minus 1/8 ln x plus O of x minus 2. Okay. And then we need to put this just to the to this formula. Okay. But again, we can use the, because here we have v to the 1/4, we can also expand this, right? Because here is this term. Let's do it. So it's x squared minus 1/4. Here is a 1/4. And that's x 1/2. Then 1 minus 1/4x squared. 1/4. Okay. And And then we expand this term. So after the expansion, we will have 1 x 1/2 plus this term. Okay. So, and the final answer, y of x asymptotic to 1 over x 1/2. Then we have this exponent. So it's e to the plus minus x squared over 2 minus plus 1 over 8 1x. And we can use the definition of the logarithm and say that this is x to the 1/2, then minus plus 1 over 8, and multiply over this, multiply by exponent, plus minus x squared over 2. Okay? This is the asymptotic solution. Okay, now let's do things more simpler and just compare this answer with the solution without 1 over 4. Maybe you can guess.
It's just exponent and without the only thing that changes is the first part, right? It's just
the solution without it would be without this correction. Just 1/2 and this exponent. Then you can see it from this or this definition without this. Okay, well, and the last part is about Stokes phenomenon. Let's look at the Stokes phenomenon. So sometimes then you solve differential equations with asymptotic methods. You can find out that the same equation, the solution of the one equation can behave differently depending on the variable. For example, for the this equation, for the other equation, you know that the asymptotics then z goes to infinity is like y, say. But when z goes to minus infinity, you will get the different form of asymptotics. So, and because of that, we can define two types of let's call it lines: Stokes lines and anti-Stokes lines. And then the variable cross the Stokes or anti-Stokes line, the solution changed somehow. And we define Stokes lines as curves where imaginary part of the s is the same as the in exponent. So this one is just a constant, but usually we use this constant as so along these lines, along Stokes line, the solution is just real without any oscillations. So just decay or special decay or both, depending on this. So if it is imaginary part of z 0, then you have just usual real solution with one term that exponentially grows and the other exponential decay. So, and the anti-Stokes lines in opposite along these lines, real part of the s is 0. Again, constant, but we define it as 0. So the along this line, the solution is purely imaginary, so without only oscillations. Right? The question is how we can find for the particular solution where is the Stokes lines and where is the anti-Stokes line. So we need to rewrite this solution in the different way. We say that z is like r to the multiplied by e to the e theta. Okay, so use the let's say polar coordinates, right? And then we can plug this to the equation to find out. So z to the 3 halves is r to the 3 halves e to the 3e theta over 2. Okay, we're not interested in this because this cannot affect, right? Only this will reveal the behavior. Okay, so for the let's calculate the Stokes lines. The Stokes lines, this the imaginary part of this should be 0, right? So as you remember, we can also write it in this way. And then to find Stokes lines, we need to find then this in what theta angle this sign is 0. So 3 theta over 2 should be
4 pi over 3, right?
pi. Yeah. So and then theta is 2 pi over 3. So it's okay. And the same we can do with anti-Stokes line, but with cosine, because we want to that real part solution should be 0. So assign theta of 2 to 0, then free theta of 2 is pi over 2 plus p n. Then theta is pi over 3 plus 2 pi over 3 n. So, and if we draw it, this is our complex plane, yeah, and so let's use different colors. So Stokes lines is this one, then 2 pi over 3, like this. This is Stokes line. And the anti-Stokes lines okay. And now we can look at this as a, for example, if we on Stokes line, whether this or this, our solution is just a real solution, sum of two exponent, one decaying, one growing. If we add this line, anti-Stokes line, the solution is oscillating. So just the sum of sine and cosine. So when we in this region, what do you think the solution look like?
Exponential exponent way.
In this sector. In this sector we have and the real part and the imaginary part. So the solution will oscillate and also decay an angle.
Okay, but the at infinity it will decay, right? The
Yeah.
exponent will win.
Yeah, yeah, of course. I mean, one will decay, the other will explode. Yeah.
Okay.
But usually in physics we set the coefficient before the explosion
Zero.
it's on 0, yeah, because it's not physical to have something like that. Okay. What else? Yeah, and in the tutorial on the limiter you have several examples on the how you can apply these Stokes lines. I mean, not imply, but in these examples you can see what stands behind these two ideas. Okay, this is connected with again W can be. How you can actually match the, so for example you have a potential, right, and this is the energy. And you know that in the classical mechanics these are two turning points. So a particle go to this point, then it stops and goes back, right? But in quantum mechanics, a particle can, go even further. So with some probability, go into forbidden zone. And the idea of Stokes lines basically helps you to understand how you can match this solution in the forbidden zone with the solution with the allowed zone. So, actually with this you can also derive the quantization law.
Right.
The integral of the action, like pi n plus 1 over 2. Yeah. So, yeah, I think this is it. If you have any question, please ask.
Thank you.
I do have a question, but about the homework. Okay. The homework.
The last one?
Yeah.
Let me check.
רוצה לשאול אותו אבל יש שאלה שקצת קצרה.
I took the phone number, but I don't know why I cannot find